This is probably close to what we're getting, so we'll just get started. Reminder of the things we finished with last time, or what we talked about last time. So remember, we're getting at the foundations of logic, and we have to use language and sentences to describe our logic and to encode our logic. So we talked about, from here on out, anytime we say the word sentence, we mean a sentence that can be classified as either true or false. So, is Frank coming to the store? That's not a sentence in this class. So anytime you see sentence, it's understood that we're talking about something that we can either call true or false. And then we talked about sentential connectives. A sentential connective is anything you can add on to a sentence and still have it be a sentence, still have it be meaningful. Any phrase, any combination of phrases, any combination of words you can add on to it is a sentential connective. So if we look at the sentence, the sky is blue, the sentential connective, Frank thinks, we can add on to that. And Frank thinks the sky is blue is perfectly meaningful. So Frank thinks is a sentential connective. Now, we're not interested in sentential connectives like Frank thinks. We were interested in very particular sentential connectives. In particular, we were interested in and, or, not, implies, and if and only if. Those are the 5 we really care about. And we have notation for each of those. That's not, that's and, that's or, that's implies, that's if and only if. And this is a precedent for which we apply those operators. Meaning, if I were to write alpha or beta and not alpha, what do I mean by that? I mean alpha or beta and not alpha. Apply the not to the alpha first, then and those two together, then we or these expressions together. You kind of think about this as like negative in arithmetic, this is like multiplication in arithmetic, this is like add in arithmetic, and these don't have good conversions. So that's the order we apply them in. Similarly, if you saw alpha implies beta is logically equivalent to not beta implies not alpha, that would mean alpha implies beta is logically equivalent to not beta implies not alpha. That would be the understood precedence from these. You do that, then that, then that, then that, then that. Okay, and now we're going to be evaluating expressions like this. You know how to evaluate them. So let's look at 2 sentences. Sentence N is going to be Newton was born in 1642. This one happens to be true. Sentence G is going to be the sentence Galileo died in 1642. This one happens to be false. So now we're going to compute something like N or G and not N implies G implies N, or implies G implies N. And I didn't leave myself any space to compute that for some reason. So we're going to have to squish here. So we're going to plug in these exact truth values. So N is true, G is false, true or false is?
True.
True. So this whole expression right here is true. So now we have true and not N. N was true, not true is
False.
false. So this whole thing simplifies to true and false. True and false is
False.
false. So this whole parenthesis here simplifies to false in the case where N is true, G is false. Let's look at this one over here. False implies true is true. So this one over here is true. And then finally, false implies true is
True.
And so this whole thing simplifies to true. The same way that I could have given you some big algebraic expression like 6 plus 4 all times negative 7 plus 19 minus 3. And you can simplify it all to one thing. We can do the same type of thing here. Okay, so that's how we would evaluate something like this, keeping in mind our precedents. And you'll get used to this precedent as time goes on. It's not something that you ever really think to memorize. It's something that you just get used to it from the language. Okay, and another thing we kind of ended with last time is talking about intuitively what a tautology is. And a tautology was a statement that was always true. That's the high-level language we used. A simple example of a tautology would be something like X or not X, if X is some sentence. Pick any sentence you want. The sky is blue. Then what I'm saying is the new sentence, the sky is blue or the sky is not blue, is a tautology. It will always be true that the sky is blue or the sky is not blue. It will always be true that 2 plus 2 is 6 or 2 plus 2 is not 6. That will always be true. tautology. That's a high-level way we think about it. Now we need to come up with a more concrete way to talk about tautologies. They're going to be a huge part of developing logic. So before we continue our discussion of tautologies, rather than just laying on high-level intuition, we first need to talk about what an atomic sentence is. So what is an atomic sentence? It is a sentence that doesn't contain any sentential connectives. So a sentence that doesn't contain any sentential connectives is atomic. Let's look at some examples. The sky is blue. Is that atomic?
Yes.
Yes. There are no words or phrases you can strip away from that thing and still have it be meaningful. It's already stripped down to its bare bones.
Okay.
Let's look at this one. The sky is not blue. Is that an atomic sentence?
No.
No, because we could get rid of the word not and it's still something meaningful. We change the meaning of it, who cares? The point is, not being here is acting as a sentential connective. We could get rid of it and it would still be meaningful. So an atomic sentence is one completely stripped of anything else you can strip of it. Strip all the sentential connectives away from it that you possibly can. And what's left is your atomic sentence.
Okay.
So this one is not an atomic sentence. What about this one? Donnie thinks cake is good. Is that an atomic sentence? No, because we can strip away this part and still have it be perfectly meaningful. Cake is good.
Yep.
So Donnie thinks here is a sentential connective. Cake is good would be the atomic sentence this is operating on. All right. 1 plus 1 equals 2 and 5 is less than 9. Is that an atomic sentence?
No.
No. And this is more how we'll typically see them. This is obviously a conjunction of two atomic sentences, that one and that one. 1 plus 1 equals 2, that's an atomic sentence. 5 is less than 9, that's an atomic sentence. This is a conjunction of two of them. So it obviously has a sentential connective and is applying to two atomic sentences. So atomic sentences stripped down to their bare bone. You can't take anything else away from it and still have it be meaningful. It's as basic as a sentence can get. If there's anything you can strip away from it and still have it be a meaningful sentence, it's not atomic. Okay, so now some intuition. We're going to say a sentence is a tautology if it is true, independent of the value of its component atomic sentences. Now, when we try to represent some sentence, we're going to try and get at its component atomic sentences and use symbols to represent those.
Okay.
And so, intuitively, what we mean by this is if once you represent each of its atomic sentences with a variable and plug it into a truth table, it's always true. So let's do a concrete example of that. If we were to look at something like this statement, I don't need this anymore. If we were to look at something like the sky is blue, or the sky is not blue. So when we represent this statement, we want to come up with a variable to represent each of its atomic sentences. This has the atomic sentence, the sky is blue, and the atomic sentence over here, the sky is blue, being knotted, and those two being ORed together. So the way we can represent this is with something like X or not X. That would be a representation of the sky is blue or the sky is not blue, this tautology. So when we're saying that this is a tautology, we mean when you represent it like this, where each variable represents an atomic sentence, and then you do the necessary sentential connectives, the resulting thing is always true. So let's see that in action. So let's say we've got some tautology, like the sky is blue or the sky is not blue, some tautology, such that when we represent its atomic sentences, it looks like this, P or not P. We're going to say that that's a tautology.
Okay.
And we're going to demonstrate that with the truth table. Maybe there was some other sentence I said, something like, if the sky is blue or the sun is hot, then the sky is blue. Is that going to be a tautology? If the sky is blue or the sun is hot, then the sky is blue.
Yeah.
Yeah, that's going to be a tautology. Here's how we would represent that. We're going to show that a tautology with the truth table. Similarly, if I said, if the sky is blue, then the sky is blue or the sun's hot. Is that a tautology? If the sky is blue, then the sky is blue or the sun is hot. Do you know if the sky is blue, then the sky is blue or the sun's hot? Yes, there you go. Yeah, so this is also going to be a tautology. We'll prove it with the truth table.
Okay.
For that first implication, what if Q is true and P is false? Isn't that true implies false?
Ah, thank you. This one will not be a tautology.
Oh, okay.
Wait, let me think. No, it will still be a tautology.
Because true implies true is true.
Wait, no, you're right. It will not be a tautology. Thank you. If you know the sky is blue, let's start with a different one. If you know, let me do a different one for this for you to see it. She's right. This one's not tautology.
Yeah.
If I were to say to you, the sky is green or the sun is hot, sorry, let me phrase it like this. If the sky is green or the sun is hot, then the sky is green. Is that a tautology?
Yeah, I see that.
Yeah, it's not.
That one.
Okay, so we'll prove is not, is. Okay. I think last time I did that as an and so that's what's mixing me up. Okay. Anyways, but let's just work with it as it is. So I happen to write one that's not a tautology here. Oh well. So we have for P and Q, for each of these atomic sentences, we have 4 possible combinations. We can have P happens to be a true sentence and Q happens to be a true sentence. We can have P happens to be a true sentence and Q happens to be a false sentence. We can have P happens to be a false one, Q happens to be a true one, and we can have they both happen to be false. Those are the 4 possible combinations with P and Q.
Okay.
Now let's do this one first. So this is ORing P with the negation of itself. So looking at P, P's true. So true or false is
True.
true. Again, true or false is true. This time, false or not false, or in other words, false or true is
True.
true, and false or true is true. Okay, now let's look at P or, so we see P or not P is always true, regardless of the value of P.
Yes.
Okay, now let's look at P or Q. This one's not a tautology, we're just doing this as a baby step to calculate these two. So, true or true is,
True.
true or false is,
True.
false or true is,
True.
false or false is.
False.
Okay, so now let's compute each of these. Let's see, true implies true is
True.
true. True implies true is
True.
true implies false is,
False.
and false implies false is
True.
true. So this one is not a tautology. It is not the case that's true no matter what its atomic sentences are.
Yeah.
Over here, we're looking at this implies this. So true implies true is
True.
true, true implies true is,
True.
false implies true is,
True.
false implies true is.
True.
Those are the vacuously true ones.
It's false plus false, but yeah.
Oh, did I read it wrong? Thank you. False implies false is true. So that one is a tautology. So tautology, not a tautology, tautology. All right, so that was our intuition. Here's what we're now going to mean by a tautology. A sentence is a tautology if and only if the result of replacing any of its component atomic sentences in all occurrences by other atomic sentences is always true. So I could take those atomic sentences and replace them with any other atomic sentences, and it's not going to change anything. Because all I was doing is I'm going to take its true or false values and switch them out with different true or false values. But no matter how I switch out its true and false values, they always come up true if it's a tautology. Now, what do we mean in all occurrences? What I mean by in all occurrences is I can't go and replace this P with one variable and then this P with another variable and expect it to be a tautology still.
Okay.
So in other words, if I were to change the variables on all these to different statements, something like this, if I were to replace those P's with now the statement X and that Q with the statement Y, would it still be a tautology?
Yeah.
Right. Yeah, that wouldn't matter. On the other hand, if I came to this and I said, now I'm going to replace P with X, and I'm going to replace this P with a Y, now is that a tautology? X or not Y? No, that one's not going to be a tautology.
Yeah.
So that's what we mean by in all occurrences. You can't replace P with one variable and then this P with a different variable. So a sentence is a tautology if and only if the results of replacing any of its component atomic sentences in all occurrences by other atomic sentences is always true. If that's the case, you have a tautology.
Okay.
Now I just gave us a pictorial way of thinking about, but this is talking about in terms of the sentences. You actually take a sentence and replace it with another sentence. So instead of talking about the sky is blue or the sky is not blue, I need to replace those with different atomic sentences. The grass is green or the grass is not green. 2 plus 2 is 4 or 2 plus 2 is not 4. Those will all be tautologies. I can't say 2 plus 2 is 4 or Frank is not big. I can say Frank is big or Frank is not big. That works. Okay, so remember this is talking in terms of sentences. I'm just writing it in terms of our notation here to help you see it.
Yep.
But always talk about sentences. Okay, now we can use truth tables to do all of this, but truth tables can eventually get pretty tedious. If my tautology had 2 variables in it, we had to have 4 rows in our truth table to determine if it's a tautology.
Okay.
What if I were looking at some statement more like, well, this one still only has 2 variables. Let's see, do I have one written up here? That one only gets to 3 variables. What if we were looking at some statement trying to determine if something like this were a tautology?
That'd be difficult, yeah.
Well, now we're going to have, how many rows would our table have to have?
6,
Since we have 3 variables here.
8.
8. So if you only have 1 variable, you need 2 rows, because that variable can either be true or false. If you have 2 variables, now you need 4 rows, because you can have true, 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 false, false, true, false, false. If you have 3 variables, now you need 8 rows, because you can have true, 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 false, true, false, true, true, and the others 4. Invert the trues and false on what I just said for the next 4. And what if you had something like 10 variables? Which doesn't seem too outrageous.
That does.
Not really.
2 to the 10.
Oh, it's outrageous now on how many rows we have.
Yeah.
I'm saying it's not outrageous that we might want to talk about tautologies that depend on 10 things.
Oh.
That's not some crazy thing. And yet if we try to do that, we're now going to have 2 to the 10, or in other words, 1,024 rows in our truth table. So truth tables are nice for proving small, little, bite-sized tautologies, but we don't want to use this to demonstrate something's a tautology in general. That would be a bad idea. We need a better way. So truth tables, they can be tedious, useful for small ones, but they can be tedious. So it's okay to use truth tables to demonstrate that some of our rules of logic are valid, but in general, that's not what we want to do. Now, for our rules of logic, oh no, this isn't for our rules of logic yet. This is just 2 useful rules to notice about tautologies. Rule number 1 to notice about tautologies. A sentence which is not a tautology may become one upon the substitution of compound sentences. Compound just means composed of atomic sentences. Compound, opposite of atomic. So by a substitution of compound sentences for atomic ones, or the substitution of the same atomic sentence for distinct ones. Give you an example of each of those. Notice here that alpha implies beta is not a tautology,
Yes.
right? On the other hand, if I do a substitution of beta for gamma or not gamma, now alpha implies gamma or not gamma is a tautology.
Yes.
Because the only way for an implication to be false is if we have true implies false. But since this piece over here is always true, now this whole implication is always true.
Yeah.
So I took an atomic sentence and replaced it with a compound sentence, and took what was not a tautology and turned it into a tautology.
Yep.
Similarly, another way I could take something that's not a tautology and turn it into a tautology is to do a substitution of the same variable for 2 separate variables. Alpha implies beta is not a tautology, but gamma implies gamma is. Is it always the case that if you know gamma, then you know gamma?
Yeah.
Yeah. Or in other words, false implies false is true. True implies true is true. It's always true. However you want to think about it. So, that's turning things that aren't into tautologies. You can, through these substitutions, make it a tautology. And then, kind of conversely, a sentence that is a tautology remains one upon the substitution of any sentence for its atomic ones, as long as you do it in all occurrences. So once you have a tautology, something like this, I can now replace my P with a more complex sentence and my Q with a more complex sentence, and it will still be a tautology. So that's what I'm doing over here. So here we have P or Q implies P, which, son of a, that one's not a tautology. Did the wrong one.
Is it?
Writing it backwards. We're doing P implies P or Q, right? This one.
Okay.
You follow that we're doing a little backwards on the implication arrow?
Could you not just turn it into an and?
I could, but I'm trying to do the same one.
Okay.
So just for the sake of doing that same one. So we already know P implies P or Q is a tautology.
Yeah.
If I let P be now the statement, X and Y, whatever that is, Frank is tall and cows eat grass, implies, I don't know, Jack likes Jill. So that's my substitution for P, and Q is not X or Y. I don't remember what I said for X or Y, but now there's not an X or Y. Then now this new resulting thing, this implies this or this, is still going to be a tautology. How can we see that? Because this piece right here is still the same as this piece right here, right?
Yep.
So if this is true, then this has to be true. If this is false, then this has to be false.
Yep.
And we still just have our four combinations. We can have these are both true and this is true, which is the same thing as P is true and Q is true. We can have these are both true and this is false. We can have these are both false and this is true. We can have these are both false and this is false when we evaluate them. And that's still handling the exact same four cases as we did over here with P and Q. So that's one trick for showing that something's a tautology. Maybe you see that rather than looking at all its individual structure, you can say, oh, this is really, if I just call this all together the statement P, all this together the statement P, and I call this right here the statement Q, and reevaluate like this, it's easier to see it's a tautology. One trick for seeing it. But the point is, once we have a tautology, like this, I can now replace my P's and Q's with any sentences I want, and it remains a tautology. So a tautology somehow in the form of that statement. All right. Now, what's a tautological implication? You can probably guess what this is. P tautologically implies Q if and only if P implies Q is a tautology. Tautological implication is an implication that's a tautology. Similarly, tautologically equivalent means that P logically equivalent to Q is a tautology. If that's always true, then we say P and Q are tautologically equivalent. Good? Okay. So that finishes the first section. On to the next one. The next one now, we get on to our sentential theory of inference. Now, we're developing our rules for inference, our rules for logic now. We want to figure out how can we determine true statements from true statements. Now we know what tautology is. We want our rules of logic to adhere to two criteria.
Okay.
The first criterion we want them to adhere to. Given a set of premises, the rules of logical derivation must permit us to infer only the conclusions which logically follow from the premises.
What does derivation mean?
We'll do derivations, but it's like a proof.
Okay.
In other words, our rules of logic better only enable you to prove true things from your premises.
Okay.
Sounds pretty intuitive, right? Let's say it one more time. Given a set of premises, set of assumptions, set of axioms, whatever. Given a set of premises, the rules of logical derivation must permit us to infer only the conclusions which logically follow from the premises. We can't conclude things that don't logically follow from the premises. We don't want that to happen.
Okay.
I know.
It's obvious here.
Kind of. We're going to catch something here in a second, but let's look at criterion 2 first. Criterion 2 is the same thing except for replace only with all. Given a set of premises, the rules of logical derivation must permit us to infer all the conclusions which logically follow from the premises.
Okay.
Okay, so those are our two big criteria. Now, we run at risk of running into some circular reasoning here. We're saying our rules of logic must logically follow Doesn't logically follow means it follows our rules of logic? Are we just saying our rules of logic must be our rules of logic?
Yeah.
That's the danger we run into here. So we need to define what exactly we mean by logically follows in terms of sentences, and then we use our notion of logically follows to determine whether a logical rule is valid or not.
Okay.
Make sense there? It's a little, what's the word I'm looking for? Subtle. It's a little subtle, the difference of what we're saying there. We have to use a concept of logically follows to determine what valid rules of logic are. And we can't use valid rules of logic to say what logically following is. We have to use some notion of sentences to capture that. Okay. So we run a risk of circular reasoning here. We need to get what logically follows is without saying it's a rule of logic. Because we need our rule of logic to logically follow. Okay. So to get this concept of logically follow, we gotta go to sentential interpretation. A sentence P is a sentential interpretation of some other sentence Q if and only if P can be obtained from Q by replacing component atomic sentences of Q with any other sentences. So you start with Q. Replace any of Q's atomic sentences with other sentences. That gives you a P. P then is a sentential interpretation of Q. Okay. Note, to be an interpretation, P must preserve the form of Q. So going back up here, we can think about this statement right here as being an interpretation of this statement.
Yeah.
Notice that it had to preserve the overall form. You still had to have an or show up in there. That or stayed right there. And you still have to have the implication show up in there. So we still had the same big picture structure. We just gave it some substructure as well. That's what we're saying here. To be an interpretation, P must preserve the form of Q. Okay. So let's look at a couple examples and see which ones are right, which ones are wrong. Get the top. Shoot. Just can't move it without moving it too much. Okay, good enough. Maybe I can also get that bottom part so we can reference it still. Barely. Okay. So let's look at some examples. Let's say that Q is a sentence. If the sun is shining, then Marianne is happy. And let's say P is a sentence. If 1 plus 2 equals 4, then snow is black or I'm a fool. The question is P a sentential interpretation of Q?
No.
Why not?
Because there's an or and that's not in Q.
There's an or and that's not in Q. But P preserves all the structure of Q.
Oh yeah, maybe.
Q just had the form if some sentence, then some other sentence. We still have if some sentence, then some other sentence. And this other sentence happened to be a disjunction. Maybe put a comma there to help make it clear.
Okay, yeah.
So the second part of our arrow, we just went from something like A implies B to C implies D or E, which is perfectly fine. We still have the overall structure of an implication. All right, what about this? Is P an interpretation of this sentence? So if the sun is shining, then it's raining or the sun is shining. And P is if 1 plus 2 equals 4, then snow is black or I'm a fool.
No.
Is this a sentential interpretation of this?
No.
No, why not?
Because 1 plus 2 equals 4 should be where I'm a fool.
Right. If I replace the sun is shining with 1 plus 2 equals 4, then over here I have to replace the sun is shining with 1 plus 2 equals 4 in order for it to still be a sentential interpretation. Since I didn't do that, that is not a valid sentential interpretation. P is not a valid sentential interpretation of, we'll call this one Q1 and Q2. It is a valid interpretation of Q1, it is not a valid interpretation of Q2. So there's a more concrete example of what we mean by sentential interpretation. Okay. So our first notion of what we mean by logically follows now. Q logically follows from P if every sentential interpretation of the new statement, P implies Q, is true. Q logically follows from P if every sentential interpretation of the implication, P implies Q, is true.
It wouldn't be a sentential interpretation of that if it's not true, would it?
If P and Q are sentences,
Yeah.
such that no matter how you switch out their structure,
So they're tautology.
well, that's basically what we're saying. P implies Q is a tautology.
Yeah.
But we're nailing down exactly what we mean by that in terms of sentential
I'm seeing that.
interpretations.
Yeah.
Right.
Yeah.
Okay. So Q logically follows from P if every sentential interpretation of P implies Q is true. Which, yeah, we're getting at P implies Q is a tautology. Which, those were the pieces I was going to put together here. So, tautology, logically equivalent to what we have written over there, a tautology is a sentence whose atomic sentential interpretations are all true. So a sentence is a tautology if no matter how you switch out its atomic sentences, it's true. Now, combining that with the note we made off screen, son of a gun, rule 2 over here, a sentence remains a tautology. A sentence that is a tautology remains one upon the substitution of any sentence for its atomic ones in all occurrences. If we combine that with our notion of a tautology here, then we get this. If every atomic interpretation is true, then every interpretation is true.
Okay.
If it doesn't matter how I switch out the atomic sentences, it's always true. Then it doesn't matter how I switch out the atomic sentences with sentences, it's always true. As long as I switch it out in all occurrences.
Yeah.
Okay, so now, finally, our final notion of logically follows, using the word tautology in it. Logically follows, what does that mean? Q logically follows from P if P tautologically implies Q. Or in other words, if P implies Q is a tautology, which you were already seeing from up here, based off of everything we said. But just trying to recombine everything we said to make it clear on one go. All right, so now we know what it means for P to logically follow from Q. Or sorry, for Q to logically follow from P. It means for P implied Q to be tautologically implied. And we know our truth table test for its tautology. So now we have a way of determining if a rule is valid. Is it a tautology? So let's look at a concrete example and see this in action and get our first rule of logic. All right, example. Premise 1. Either Mary gives Peter his toy or Peter is going to cry. Premise 2. Mary does not give Peter his toy. What can we conclude from that?
That Peter cries.
Peter's going to cry. Okay. Doing the encoding of this, premise 1 was either Mary gives Peter his toy or Peter's going to cry. So we'll represent that as M or P. M is Mary gives Peter his toy, P is Peter's going to cry. M or P, we've now represented it atomically.
Yeah.
Okay, premise 2 is Mary does not give Peter his toy. That's not M. Right?
Yeah.
And what we're saying, our intuition is telling us that if you know M or P, and you know not M, you're able to conclude
Not P. Or yes,
P.
P.
And now, kind of ignoring these sentences for a second and just thinking about it, you can also pretty much see it. This says, I know M or P is true. This says, I know M is false.
Yeah.
Therefore, P had to be true. And now, this is a small enough rule of logic that we could easily build a truth table for it to demonstrate it. We could have true, 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 false, false, true, false, false. And I decided to just basically do it all in one go. So M or P and not M. Let's take this one at a time. True or true.
True.
And false.
And false. True. False.
False. Ending with false is always false, right?
Yep.
Alright. True or false is true.
Yep.
And false is false. Okay, let's look at this one.
Why? Yeah. Keep going.
False or true is true. And true is true.
Yeah.
And then finally, false or false is false. And true is false. Right? Now, what we were saying is, if you know this and this, then you know this.
Okay.
That's written out right here. We're saying this premise and this premise together imply this premise is what's true.
Oh, trying to make it a tautology.
This is what we're claiming is a tautology.
Yeah, okay. I see.
That's how we're going to say it's a valid rule of logic. Because then we can say this logically follows from this. How do we know that? Because it's tautologically implied. And we're demonstrating that with the truth table. And I tried to justify to you why truth table works as long as we made sure that these represent atomic sentences. Okay. So now let's go with this. So we have false implies true is
False implies true is true.
true, vacuously true. False implies false is
True.
oops. False implies true is
Still true.
still true. True implies false? No, we're doing P. Sorry. I think I messed up on this. False implies true, true. False implies false, true. True implies true, true. False implies false, true.
That's tautology, yeah.
So it is a tautology. So we now know that M or P and not M implies P is a valid rule of logic. Or writing out with alphas and betas, we just found out that alpha or beta and not alpha implies beta is a valid rule of logic. Okay. Now another way that we can think about what criterion 1 says over there, if we think about in the negation. So 1, it says, it's a valid rule if the conclusion logically follows from the premise. We can think about how it also tells us if it's an invalid rule. So if a new rule of logic allows us to derive a false conclusion from a true premise, we reject it. That's another way we can think about criterion 1. So one way to think about criterion 1, where do I have it written?
Criterion 1, right there in the middle.
Under major criteria in the middle.
Oh, right here. Alright, we'll be coming back to those a little bit. Criterion 1 says, given a set of premises, the rules of logical derivation must permit us to infer only those conclusions which logically follow from the premises. So if it does that, then we can accept the rule of logic. If, on the other hand, another way of thinking about that in the negation is if a new rule of logic allows us to derive a false conclusion from a true premise, reject it. In other words, if a rule of logic enabled me to infer if x equals 2, then 2x equals 97, reject it. Whatever rule I was using that let me do that is a bad rule. So we can also think about how it helps us reject bad rules of logic.
Okay.
So, let's give this a shot. Let's look at another rule of logic and see if it's a valid rule or not. So what about the rule? Beta and alpha implies beta tells us alpha.
We're trying to figure out if it's tautology.
Yeah. Is that a valid rule of logic? Or are we cheating? Now, if we can come up with one case where it doesn't work, then it's invalid. So we try something out. I need to come up with an alpha and beta where this is true, but this is false.
That's not.
If I can do that, then I have true implies false, which is false.
That's false.
And so it's not a tautology. I basically come up with a counterexample.
Yeah.
That's essentially what we're doing here. So this is not a tautology. The way I'm going to prove that is with the counterexample, rather than writing through a truth table.
That's easy. Yeah.
Okay, so alpha is going to be, I'm in Alaska. beta is going to be I'm in the US. And think about this as actually referring to me. I should have wrote Donnie rather than I'm.
Okay.
We're talking about me. That's I'm. Okay. So is it true that I'm in the US?
Yes.
Yes. Is it true that if I'm in Alaska, I'm in the US?
Yes.
Okay. So it's true that I'm in the US, and it's true that if I'm in Alaska, I'm in the US. Is it true then that I'm in Alaska?
You don't know. Not right now yet.
No, yeah, we're saying me right now here. Yeah, that's why I'm saying should have said Donnie. Right. So we're talking about me right here, right now.
Okay.
The antecedent was true, the conclusion was false, therefore this is not a valid rule of logic. Throw it away. I was able to come to a false conclusion, I'm in Alaska, from a true premise. So I'll read this one more time. If a new rule of logic allows us to derive a false conclusion from a true premise, reject it. So we reject that rule of logic, and that's not a valid one. Alright, let's play for a little bit. Maybe swap my alpha and beta here. So we got the alpha there and beta there. What about that? Is that a valid rule of logic?
Alaska.
Well, that's just one example. Maybe it works with the sentences I picked. The only way to know for sure it's a valid rule of logic is to know that it's true regardless of the sentences you plug in there. Which is why the truth table can be useful. But sometimes you can also just see it. Let me say it out loud and see if you just see it. If you know alpha,
Okay.
and you know alpha implies beta, do you know beta? If you know that alpha is true, and you know that anytime alpha is true, beta is true,
Okay.
do you know beta is true?
It changes.
Let's try it again. Alpha implies beta means if alpha is true, then beta is true.
Okay.
Right?
Yeah.
So if you know that alpha is true, what do you know?
Beta's true.
Okay, so you know if alpha is true, then beta is true,
Yeah.
and you know alpha is true. Do you then know beta is true?
Yes.
Yes.
Okay.
Does it still feel weird?
Because it's an and, it's not just alpha.
I know alpha implies beta,
Yeah.
and I know alpha,
Yes.
so I know beta.
Okay.
Okay, this time, set it up as a...
That makes sense to me. Actually.
Okay. If we set up some if we made this true now, so now it's not me here right now. If it were true that I was in Alaska, and it were true that my being in Alaska implied I was in the US, would it be true that I was in the US?
Yes.
Yes.
Yeah.
Okay. Or you could build out a truth table to test this as well. Right?
Yeah.
So, the truth table still works. When we have small ones. When they get too big, the truth table becomes tedious, and actually we'll get to the point where we prove things that you can't prove with the truth table.
Okay.
So, truth table is good for relying on really basic rules like that, and then we'll use really basic rules like this in our derivation. And we can decide if we ever get stuck on a rule. So I'll say, and using this, here's a rule. If we get stuck on no rules like that, I'll always be able to go to the side and just scratch out a truth table for us to see it. Okay. So that was a lot about criterion 1. But what about criterion 2? What did criterion 2 say? It said, given a set of premises, the rules of logical derivation must permit us to infer all the conclusions which logically follow from the premises. Does criterion 2 really add anything?
No.
No, not really. Let's see why it does. Imagine I said, okay, here's our only rule of logic. Alpha implies alpha.
Okay.
That's our only rule of logic. It meets criterion 1, right?
No.
It meets criterion. This is definitely,
Yeah.
alpha definitely logically follows from alpha.
That is a tautology.
So this is a valid rule using criterion 1.
Yeah.
So I said, wonderful, here's your only rule of logic. Have at it.
No. It's what? Why is it the only rule?
What if I did say that? What could you do with it? Almost nothing. You see how just having this rule is useless?
Yeah.
So this meets criterion 1, but doesn't meet criterion 2. What does criterion 2 say? It says, given a set of premise, the rules of logical derivation must permit us to infer all the conclusions which logically follow from the premises. If we only had this rule of logic, we couldn't determine all the conclusions.
Well, given that set of premises, there's only one conclusion that will follow.
Look, this is true, right?
Yeah.
I could never conclude this if this was the only piece of logic I could use.
Yeah, but you can just change it to set of premises. It never says all the set of premises.
What?
Given a set of premises. And then just
Given a set of
premises.
premises, I can always use this type of thinking. Okay, maybe we'll come back and say more about that when we're actually doing a proof.
Okay.
And I'll show you how if we limit ourselves to this, we get stuck in the proof and we can't prove something that logically follows. Actually, we can do it right here. Here's our premise, here's our premise. Using these two premises, conclude that if this is our only valid rule of logic.
Where did that ever turn into the only valid rule of logic?
It's not.
In
We're saying that we need a requirement that says you can't say that this is the only rule of logic.
But the premises of that and the premise of that is different. So why did they?
This isn't any premises. This is saying a rule of logic.
Premise is alpha. What is premise?
Premise is just your starting point. I give you some random argument, like, here's two premises. What can you conclude from these premises? So you have these two premises. Using this particular rule right here, you're able to come to this conclusion.
Okay. Yeah.
So with these premises, together with this rule of logic, you were able to come to this conclusion.
Mm-hmm.
With these premises, if this were your only rule of logic, you cannot come to this conclusion.
Okay.
So criterion 2 is saying you can't do something like say this is our only rule of logic. Because there's things that are true that we would not be able to conclude from our premises. These premises do logically entail this. So our rules of logic better enable us to conclude this from this.
Yeah.
That's what premise 2 is saying. So read it, or criterion 2 is saying. Read it one more time. Given a set of premises, the rules of logical derivation must permit us to infer all the conclusions which logically fall from the premises. Since this does logically fall from this, our rules of logic better enable us to determine this from
That makes
this.
sense, yeah.
That's what we're saying. Okay. Yeah, it's a bit hard to follow exactly what we're saying since we're so low level. And you'll get more comfortable with it when we jump into actual proofs. Which will be now. Okay. So now we'll jump into our first proofs. Get that going just so we can read the prompts from the book that we're doing. I'll read these and then move the camera over so that we can see where I'm writing. So, these are our 3 sentential rules of derivation. These are our 3 rules that we can use in constructing a derivation. A derivation proof, same thing. In constructing a proof, there's these 3 rules, and just, well, for now, just these 3 rules.
Okay.
Rule number 1, or rule P, is we may introduce a premise at any point in our derivation. Rule T is we may introduce S, some sentence S, in our derivation if it is tautologically implied by the conjunction of preceding sentences in our derivation. And then rule CP is the weirdest, so we'll come back to it after we get comfortable with these first 2. So let me give you concrete examples of these first 2, and then we'll go back to rule 3 there. Ew, I am not going to have space.
For rule T, is there any specific reason you said conjunction and why we wouldn't use like disjunction or?
Yes, exactly like what we did here. To come to this conclusion, you can join this with this and saw what they implied. It's a conjunction. When I say this statement and this statement together imply this thing, you're saying this and this imply this. So yeah, it is specifically the conjunction. I really don't want that to be cricket like that. Maybe we can get crazy. Alright, not the worst thing in the world. Let's open this. It's just the things we're proving are going to be big paragraphs, and I don't want to write them all out. Hopefully my fingerprint works with the chalk. Alright. Hopefully this works. Okay, so the first thing we're going to do a proof of is example 1. If there are no government subsidies of agriculture, then there are government controls of agriculture. That's premise 1. If there are no government controls of agriculture, then there is not an agricultural depression. That's premise 2. There is either an agricultural depression or an agricultural overproduction. That's premise 3. As a matter of fact, there is no overproduction. Therefore, there are government subsidies of agriculture. Okay, that's kind of a bit of a mouthful of an argument to follow, right? So let's break this down and see if we can understand it. So, number 1 is, if there are government subsidies of agriculture, we'll use an S to represent that atomic sentence. Government subsidies of agriculture. Then there are government controls of agriculture. So we'll encode that sentence as S implies C. Subsidies implies controls.
Yeah.
That's what that says. Okay, next one.
Wouldn't you say not? Or a not sign for the S?
Oh, did it say not?
If there are no...
If there are no government subsidies. Thank you, yes. Good catch. Not subsidies implies controls. Right?
Yeah.
Okay, that's another reason I wanted to have it up here. You can catch my mistakes. If there are government controls of agriculture, there is not an agricultural depression. So 2 is, controls implies not a depression, right?
Yeah.
Okay, number 3 is, there is either an agricultural depression or overproduction. So I know that there's a depression or an overproduction. And then 4 is, as a matter of fact, there is no overproduction. So 4 is, there is not an overproduction. Now we're trying to conclude, therefore, there are government subsidies of agriculture. So we're trying to conclude that S is true from these premises. You with me? Okay, so that's reading the sentences. Now we don't really care about the paragraph. And get you comfortable with the notation of how we do a proof now. So this right here was a premise. So we'll put a P here. And over here, we're going to put all the premises it depends on. Kind of weird. This will make sense as you get used to it. So this was a premise, and it only depended on itself. This was a premise, and it only depended upon itself. This was a premise. You'll get used to this in a second. And it only depended on itself. This was a premise, and it only depended upon itself. So if I know these 4 things are true, can I conclude that S is true? That's what we're trying to do. You with me? Okay. So now, what are we going to do for line number 5? What can I conclude given all this information? Well, notice that if I know D or O, and I know not O, what do I know?
D must be true.
D. If I know D or O is true, and I know O is false, then D must be true.
Why do you know one of those are true? Can't they both?
We are using the exact rule we had written right here. If I know alpha or beta, and I know not alpha, then I know beta. D or O and not O implies D. That's the rule I'm using. So to make very explicitly the rule I'm
That
using.
makes sense, yeah.
Okay, just want to be super explicit. So right here, we are now going to conclude D. This was tautologically implied from lines 3 and 4. With me so far? This and this tautologically imply that. we prove that this implication is a tautology. We're using this rule of logic. So that was the first rule of logic I used in this proof.
Yeah, I see what you're saying, yeah.
Okay, so line 5 is tautologically implied by 3 and 4. And now the premises line 5 depends upon are the premises that 3 and 4 depended upon. Line 3 only depended upon premise 3, and line 4 only depended upon premise 4. So if you know 3 and 4, then you can conclude line 5.
Okay.
With me so far? Now we just barely used, here introducing these lines, we were using rule P. We may introduce a premise at any point in our derivation. Here's our derivation. I just introduced the P's. Because to start with, that's the only thing I can do is introduce a premise. So introducing a premise, I use rule P 4 times. 5, I use rule T. We may introduce S, in that case that's D, in our derivation if it is tautologically implied by the conjunction of preceding sentences in our derivation. This and this tautologically imply this. Therefore, introducing line 5 is totally valid.
Yeah.
Follow that? That was using rule T. Now, let's keep going with this. Okay, now I know D. What can I conclude from D?
That C is wrong.
That's not C. Wonderful. That one's kind of a harder one to see if you haven't done a lot of logic before. But this is tautologically implied by D and by 2 and 5. And so now we've used premise 2, 3, and 4.
Not
5 isn't, this is just keeping track of the premises we used.
5? Oh, yeah.
Okay, so let's see how this one came from this and this. We know here that if C is true, D is false.
Yeah.
But we know D is true.
Yeah.
So C can't be true. Because if C were true, then D would be false. But D is true. Or we can think about the contrapositive of this. What's the contrapositive of C implies not D?
D implies not C.
It's D implies not C. Not C. You take the negation of both sides and flip the order.
Yeah.
The way you typically see that is alpha implies beta is logically equivalent to not beta implies not alpha. This implication is the same as this implication. So we took this, alpha was C, beta was not D, and we wrote it this way. We have not D implies not C. However it clicks. Sometimes just saying out loud is enough to make it click for you. But if anytime I use a rule that you don't like, they're always going to be small enough that we can quickly do a truth table if anyone wants to see it. Because we'll keep these rules bite-sized. Okay. So now we know not C. Okay, so now what can we conclude?
Yes, S.
We can conclude S. So now we can conclude S. This is tautologically implied by line 1 and line 6.
Yeah.
We know that if S is false, C has to be true. But C is false, so S had to be true. Because if S were false, C would be true. But it's not. Okay, so we were able to conclude S, and now that was using premises 1, 2, 3, and 4. This tracking premises seems a little bit awkward. You'll understand more why as we do more of it. But so this is now how we do an actual derivation, an actual proof. This is proof with a capital P. This is way more thorough than the types of proofs we do in math, which are all wordy and stuff.
Yeah.
Everything is crystal clear.
But is there any place you'd have to like define what S and C are? Or are we just...
They're statements. They're things that are true or false. So if you know this, and you know this, and you know this, and you know this, then you know this. Now, I know that's a lot of new notation for you guys here. Is the top going off the camera?
No, it's not.
Okay, thank goodness. Lost my train of thought. Oh, so this seems like a lot of notation. It might seem kind of scary to try and do something like this on your own. But imagine now if we tried to prove this as a truth table. What did we just barely show? We just barely showed that not S implies C, and C implies not D, and D or O, and not O implies S is a tautology.
Yeah.
That's what we did. You don't want to do a truth table for that.
Yeah.
That blows up. This is a lot more clean, a lot easier to follow. And you can see where you're using the logic. Okay, so that was our first example of a proof. Probably should have compared it to the authors to make sure we didn't make a mistake. I don't think we made a mistake. With all of us looking at it, if I would have made a mistake, I think one of us would have caught it. Alright, now let's do a bad proof right here to drive the point home about rule P. So let's say I want to show that Q logically follows from, what did I do? P or not P, or P or Q. So we did with a truth table that this doesn't work, but it seems like this is kind of telling us that it works if we cheat and use these rules of derivation. So you'll see what I mean here in a second. So I'll say one is I introduce my premise, Q, as a premise, and it only depends on itself as a premise. Then I introduce, rule 2 says, or rule P says, I can introduce a premise at any point I want. Any premise I want. There's no restriction on the premises I can introduce. So I'm going to come along and I'm going to introduce not P as a premise. Nothing wrong with that. That's a premise. Okay, and it depends on 2. Now, 3, what do I know?
I'm confused why Q is your premise and not P or Q.
Oh, thank you. Thank you.
Oh.
Because I wrote it first, and so must be the premise. Q logically follows from P or Q. So I have P or Q as a premise, and I have not P as a premise,
And we're trying to prove Q.
and so I put those together and I get Q, right? So Q, which is tautologically implied by 1 and 2. Now this is kind of a simple proof, but this is why we keep track of what the premises depend on. This is telling us what we proved. We proved that this logically follows from these. We did not prove that Q logically follows from P or Q. We proved that Q logically follows from P or Q and not P. That's why keeping track of your premise here is very important. What we're saying is you've shown that this logically follows from these premises. And so you can't use these rules to somehow cheat and start proving things that we knew you couldn't prove.
Are you saying there's nothing wrong with that?
I'm saying that this proof does not show that Q logically follows from P or Q.
Yeah, it doesn't. Okay.
What it showed is that Q logically follows from P or Q and not P. Okay, Q logically follows from those. Yes, that is the case. And that's what we proved here. So this rule of you can introduce a premise at any time, it's a valid rule, but you have to keep track of what your premises, your conclusions depend upon. And that's how you interpret it. Okay. Let's do another wordy example, one that introduces this rule CP. Open that back up. And look for example 2 now. Did I pass that? Or are they still just explaining that? Introducing the rules, we just already did that. Rule CP. Okay, second example. We'll try not to cheat. Okay, so let's look at the second example now. If cards are third, then if Dodgers are second, the Braves will be fourth. So let's try and get that one. That said, if cards are third, we'll represent that with C. Then, and then if I understood it right, there was another implication they applied. If cards are third, then if dodgers are second, we'll represent that with a D. Then braves will be fourth. We'll represent that with a B. So that's premise 1. If C, then if D, then B. Okay. Next, either the giants will not be first or the cards will be third. Either not the giants will be whatever it said, or the cards. Let's read that again. Either the giants will not be first, or the cards will be third. Okay. In fact, the dodgers will be second. So 3 is, we know, D. Therefore, if the giants are first, then the braves will be fourth. So the thing we're trying to include now is, therefore, G implies which one?
B.
B. So that's what we're trying to prove. Make sense? All right. Let's shut that off and get at it. Okay, so first off, this is our premise, and it depends just upon itself. This is a premise, and it depends just upon itself. This is a premise, and it just depends upon itself.
Is there ever a premise that does not just depend on itself?
No, every premise just depends on itself for its validity.
Okay.
How do I know that this premise is true from this premise?
Yeah.
Okay. Now, here's where we gotta use the rule CP. If we want to derive S from R, sorry, read that word. If we can derive S from R and a set of premises, then we can derive just S, R implies S, from the premises alone. So if I can get from my premises, so let's say we have 3 premises, P1 and P2 and P3 and R implies S. If I can show that that's the case, that will be logically equivalent to showing P1 and P2 and P3 implies R implies S. If it's always the case, anytime P1, P2, P3, and R are true, you get S, then you know that if P1 and P2 and P3 are true, it will be the case that if you have R, you have S.
Okay.
Make sense? That's what rule 3 is saying.
Implies is distributive.
No. Not implies it's distributive.
Okay.
Think about the logic of the words. If I know that P1 and P2 and P3 and R imply S,
Okay.
if knowing those 4 things are true tells me that S is true, then knowing P1 and P2 and P3 tells me that if R is true, S is also true. So we go from this to this. So we go from saying these 4 premises tell me S to these 3 premises tell me R implies S.
Okay.
You with me? And what we're trying to show is G implies B.
Would you also do that except replace P1 with R and R with P1?
Yeah, it doesn't matter what the variables are.
Oh, okay.
They're just variables. I was just saying this is a special premise.
Yeah.
Okay, that's what this is saying. If we can derive S from R and a set of premises, so we can get S from R and a set of premises, then we can derive R implies S from just the premises alone.
Okay.
That's what it's saying. Follow that? Okay. So 4 here is going to be a little bit weird. We're going to introduce G as a premise, but I'm going to put over here that it's a conditional premise. Meaning I promise I'm going to get rid of this as a premise later on.
Okay.
And we indent ourselves to remind ourselves. And so this just depends upon itself. 4.
Why is the G so far out?
Why is it so much indented? Because it's going to be a conditional premise. You'll see as I continue my proof.
Okay.
So now I have these 3 premises, and then this what I'm going to call a conditional premise.
Okay.
And it's one that I'm telling you, I promise, using the trick we just showed, I'm going to eliminate it as a premise later on. But for now, we'll just treat it like a regular premise. But once we introduce it, I'm going to keep my proof indented until I get rid of it. And then I'll unindent my proof. Okay, so now 5. Alright, so if I know all these, let's see, what can we conclude?
We can conclude that C is true.
We can conclude not C is true.
Yeah.
If I know G is false or C is true,
But G is true, so not G is false.
oh, thank you.
What?
Yes, she's 100% right.
Why?
I know that G is false or C is true.
Yeah.
Is G false?
No.
So C is true.
No.
I know G
Oh,
is
yeah.
false or C is true.
No.
I know G is false or C is true.
Yes.
One of those has to be true.
Yes.
Is G false?
No.
Then C is true. Alright. I know, it was weird in my head for a sec too. But we can quickly write this out. So we'll do G, C, not G or C. Maybe we can do a bunch all in one go. Not G or C, and G. And then finally, not G or C, and G implies C. If it's a valid rule, this better be a tautology, right?
Yeah.
And of course we have true, 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 false, false, true, false, false. Okay, let's look at this one. False or true is
True.
true, and true is
True.
true. Next one. False or false is,
False.
and anything is still going to be false.
Yeah.
Okay. True or true is,
True.
and false is.
False.
And then finally, true or false is
False.
true, and false is going to be false.
False.
So, false. Okay. Done with the hard part. So now, let's see, imply C. True implies true is. True, false implies false is.
True.
False implies anything. False implies anything. True, 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 true. Okay, it's a tautology. So we're using a valid rule of logic. So, what we just barely showed is that 2 and 4 tautologically imply 5. Right? So far this depends on premises 2 and 4. You with me? What's holding you up?
The same thing.
The same thing. Alright, let's try to say some language one more time.
Can I just say?
I know, let's set this up as markers. Where's my green marker? We use chalk. I know either, let's see, G will be Donnie's holding a pink marker, or pink chalk, and C will be Donnie's holding a blue chalk.
Okay.
I tell you, either I'm not holding a pink chalk or I'm holding a blue chalk. Is that true?
Yes.
I'm not holding a pink chalk or I'm holding a blue chalk.
Yeah.
So you know I'm holding a blue chalk.
Yeah.
So I made G true, I made C true. If you knew that this is true, this is true. I don't think that helped. I think the easiest way to say it is the way I said before. We know either G is false or C is true.
Yeah, it's not inclusive, or it is.
G is false or C is true. It can be inclusive. This can be false and this can be true. But either this is false or this is true.
Yeah.
Okay, is this false?
G is true.
Right, so is this false?
G is true. What?
Is this false?
No.
So this is true.
Well, okay, but then you can say G is true, so C is false. I mean, how do you know which way to look at it?
No, this says either G is false or C is true. That's all it says.
And G is false.
No, G is true.
False.
G is not false.
So G is not false, so G is true. So C must be false.
No. Is the statement not G true?
No.
It's false. This right here, if we were to plug in the value, we now know this is false. We now know false or C.
That's so obvious.
False or C has to be true. The only way for that to be true is if C is true.
That's really obvious. You're not replacing it. Okay. I was thinking about replacing it.
I don't know what that means, but
Okay.
if it clicks, it clicks.
Okay, good.
Wonderful. Okay. So this, together with this, tautologically imply this. All right. So we got that. All right. So now we know C. All right. Now what can we conclude?
That D implies B.
That D implies B. Perfect. We know C is true. And premise 1 is if C is true, then D implies B. So this was tautologically implied by lines 5 and 1. So by 1 and 5. Then we knew this. And so now what are all the premises we depend upon? We depend on the premises 1 and 2 and 4. So now we're using premises 1, 2, and 4. Right? Now what can we conclude?
That B is true.
That B is true.
Yeah.
We're using 3 and 6 to conclude B. So 7 is that B is true. This is tautologically implied by 3 and 6. And now we're using the premises 1, 2, 3, 4. All right, so what did I just really show?
That if G was true, B.
I showed that if, we'll call this premise 1, premise 2, premise 3, and R. I just really showed that if P1 and P2 and P3 and R are true, then we were able to conclude this was our S. Remember, we're trying to show this implies this.
Yeah.
So if your premises together with R implies S is true, from that you can conclude that P1 and P2 and P3 implies R implies S. So I'm about to use that rule now. So 8, we now conclude, we get rid of our indent, we say G implies B. This ends our conditional probability, starting on line 4 through 7. And now, we are no longer assuming G is true. So we remove premise 4 from our set. So now we're only using premises 1, 2, and 3.
Why are you not saying G implies G implies B? Because R implies S, and S is G implies B.
I got rid of R as a premise,
Yeah.
and added R implies S as a conclusion.
So what's R now?
R is still just G in this case.
So why is it not G implies B?
We conclude, this is our conclusion. Conclusion, conclusion.
Where's the R?
Premises.
Yep.
G is always R. R doesn't change.
S is not B.
Okay, let's make this very clear. S is B.
S is G implies B.
Now,
Oh, what?
let's replace all that with G's and B's. Okay. What I did up to here, if you stop on this line, what did I show? If you stop on this line, I showed premise 1 and premise 2 and premise 3 and G tell us that we can conclude B.
Yeah.
That's logically equivalent to this.
Yeah.
Premise 1 and premise 2 and premise 3 tell us that we can conclude G implies B. That's going from here to here.
Yep.
Okay. And so that's using this rule.
I thought S was G implies B, not just B.
Okay. Good. All right. that gives you a taste of the test. Now, I said that come about 8:30, we would open it up to homework. I don't know what you guys want to do homework-wise. Homework problems. You want to go through the homework problems? You don't want to go through the homework problems? You want you to go through the homework problems? You want me to go through the homework problems? You want to do them here in class, but turn off the camera?
It's been a while since we've done that.
I don't know. What do you guys want to do homework problem-wise?
I would like to.
Yeah, why don't we do it?
You want the students to come up and do it? All right. So we'll go to chapter 1 homework and start just going through the problems. You want this in lecture? You want it recorded?
I mean, I don't really care.
Yeah, I don't have a preference either. I don't see myself going back and watching it. Like
Yeah, I don't think it's
specifically
gonna
the
help.
homework one, maybe the lecture.
Huh?
I don't think it's gonna help me.
Doesn't matter to me, but doesn't matter to you guys. Better to regret too much information than not enough information.
It's true.
All right, so let's go over the first problem. Construct specific counterexamples. I didn't check if we were back in chapter 1. Good thing, because we weren't. Chapter 2, okay, chapter 1 homework's right here. So going all the way back. Let's do these exercises. Problem number 1. A classical example of a non-truth functional connective is that of possibility. For example, the sentence, "It is possible that there is life on Mars," is true under any liberal interpretation of the notion of possibility. But then the sentence, "It is possible that there is not any life on Mars," on the other hand, is also true. So, if we think about "it is possible" as a sentential connective, and we think about "it is possible that" as a sentential connective, and we think "there is life on Mars" as our sentence, then, with this as our sentential connective, we would want to say that "it is possible that there is life on Mars" is true, but if I negate this, we still want to call it true.
The whole sentence.
True or false? It is possible that there is life on Mars.
True.
True or false? It is possible that there is not life on Mars.
True.
True. So it's true independent of what that value was. Kind of weird. Now let's look at another example. It is possible that 2 plus 2 equals 5.
No.
No. So, just by knowing whether this is true or false does not enable you to determine whether the whole thing is true or false. If I gave you a true atomic sentence, you can't tell me if the whole thing is true or false. Maybe it's true, maybe it's false. Depends on the sentence you gave me.
Okay.
So, "it is possible that" is not a truth functional sentential connective.
Yeah.
Okay. We're giving examples of bad ones that we would never use. And then they build out a whole truth table for this. Never really explain this problem. But you already get the picture. Give examples and analysis to show that the following are not truth functional connectives. So they're saying these other two are not truth functional. If the sky's blue, if you know it's true that the sky's blue, do you know it's true that Mr. Smith believes the sky's blue?
No.
But you know it's false that he believes the sky's blue.
No.
No, you can't determine the truth or falsity of it when we attach that on. So that's not truth functional sentential connective. It is necessary that the sky's blue.
Yes. No.
That was kind of weird. It is necessary that who just barely won the Super Bowl? Chiefs.
Jeez.
It is necessary that the Chiefs won the Super Bowl. No, they could have lost. So just because I gave you something true here doesn't necessarily make it true. On the other hand, I say it is necessary that 2 plus 2 equals 4. You'd want to say yes. Is it necessary that 2 plus 2 equals 4? Yeah. Is it necessary that the Chiefs won the Super Bowl? No. So, not truth functional. Not very interesting. Okay. Which of the truth functional connectives introduced in this chapter is an approximate synonym of the connective unless. Alright, what does it mean to say unless? Let's think of an example of a sentence. I will give you an F unless you bribe me. What am I saying in terms of the truth functional sentential connectives we know and love?
Not very honest teacher.
No, restate that in terms of our sentential connectives we know and love. So restate that either using the word and or if ... then ... Sorry, can't really do comma separated. What's our other ones? Not, and then if and only if, which we'll do if with two F's. So they're saying restate. What does unless mean if you had to pick one of these for it to mean? If I say alpha unless beta, what am I saying? I will give you an F unless you bribe me. What does that mean? If what?
P if not alpha? Or sorry, if B not alpha, then not alpha?
You're saying if beta, then not alpha?
Yes.
Let's try that. I will give you a F unless you bribe me means if you bribe me, then I won't give you an F. Right?
Yeah.
There you go. Now you know how to interpret the word unless.
Is that the only meaning?
What else could it mean?
If I give you an F, then you will not bribe me. And you did not bribe me.
So you're trying to say if not alpha, or sorry, if alpha, then not beta,
Not beta.
which is just contrapositive of this. So yeah,
Huh?
there's a lot of ways you can state an implication.
Okay.
So yeah, it also means if you give me money, then I won't fail you. Perfect. All right, so that's what unless is. I think that's all that was. Translate the following compound sentences into symbolic notation using letters to stand for atomic sentences. All right. Ew, I wonder if I'm off the screen. Probably just right over it. Okay, let's do I. Let's do A. I started reading either as I said it. It came out a letter. Let's do A. Either the fire was produced by arson or it was produced by spontaneous combustion. How would we represent that symbolically?
Just like an A or C.
A or C. It was either arson or it was spontaneous combustion. Okay, maybe this one will be harder. If the water is clear, then either Henry can see the bottom of the pool or he is a nincompoop. Kind of dates the book.
Yeah.
Alright, what's this one? How can we represent as letters?
Without the parentheses and stuff, do we know, like, is the or part of the second half of that?
The comma is what's given away there.
Okay.
So the consequent of that implication is a disjunction. The disjunction is in the consequent.
Okay, so we just have to go off commas for stuff like that?
Yeah, kind of.
Okay.
Just have to know how to interpret it. Usually the either there really helps. Then either means I'm going to give you two things now. So that's also really hinting.
Right.
So how would we represent it?
If A, then B or C.
We would represent it as water is clear. What should we use for that? Clear water implies what?
B.
Implies we can see the bottom or use a nincompoop. And if you're not clear on the parentheses, it's parentheses like that. We're saying this implies this or this. Not this implies this, or we have that. Good. All right. Either John is not here, or Mary is, and Helen certainly is. All right. What is that sentence saying?
Not J
Not J
or N.
or N.
And then that's in parentheses. I don't know if that matters. And then
Parentheses.
H.
And what?
And H.
And H. Either John is not here or Mary is, and Helen certainly is. That's correct representation. And then, yes, we have to have the parentheses there because remember, and takes precedence over or. By the way, it's that way in programming as well. When you do your ands and or conditionals, and takes precedence over ors. All right, next. If there are more cats than dogs, then there are more horses than dogs, and there are fewer snakes than cats.
What do you use for more?
Maybe you're overthinking it.
If C is greater than B.
No. 9 is greater than 5 is an atomic sentence.
Oh. So if C.
If C, so cats are more than dogs, so I don't know how to write if C. You mean just write C? Okay.
Oh yeah. C implies H and S.
Then there are more horses than dogs, and there are fewer snakes than cats. Right. And in case you need the parentheses, it's parentheses like that. Okay. That's what I have to watch so far. Oh, a lot more of those. You want to do more of those or move on to 4? You like it? You like it's useful?
I'd
All
like
right.
to move on.
You want to move on? All right, let's move on. 4. In the following examples, determine the truth value of the compound sentence from the given truth values of the component sentences. All right. So we know Galileo was born before Descartes is true. We know Descartes was born in the 16th century is true. We know Newton was born before Shakespeare is false. I don't even know who Racine is. Everyone else was a compatriot of Galileo is false. All right. So now let's determine the truth or falsity of these. If Galileo was born before Descartes, let's see, Galileo was born before Descartes is true. So we have true implies Newton was not born before Shakespeare. So not Newton was born before Shakespeare, not false. Maybe that's a bad way to do it all in one go. Let's first think about this also as being G, D, N, R. And first let's write it down symbolically the way we were doing the other ones, and then we'll calculate it. That'll probably be easier. So if G, then not N. Right? That's what the first one's saying. Now we know that G is true, and we know that not N, N is false, so not N is true. And true implies true is true. So A, this whole thing evaluates to true. Alright, next. If either R or N, if R or N, then D, right? For B, if R or N, then D. So let's see, R is false. So we have false or N is false. Implies D is true. False or false is?
False.
False implies true is?
True.
So this whole thing is true. So it is true that if either Racine was a compatriot or of Galileo, or Newton was born before Shakespeare, then Descartes was born in the 16th century. That's true. It's actually true. All right, next one. If not R, then either not D or N. Then not D or N. Did I do that one right? All right. So let's see. Not R is true because R is false. Not D is false. N is false. False or false is false. True implies false is
False.
false. So this whole thing is false. Okay. On to the next one. I don't know. One of you guys want to do it?
Sure.
Sure. All right. Come to number 5.
What is it?
Huh?
What is it?
How would I know? I think I memorized the book.
Yeah. What
So let N, W, and C be all those statements. And in case you don't know, N and W are true, C is false. Which of the following sentences are true?
N or C is true.
True.
Okay.
Right, true or false is true.
And C are false.
Good.
Is that supposed to be not? No.
Yeah. Oh yeah, sorry. His notation is a little bit different. He's a bit outdated. So he does his ands like that, and he does his nots as negative signs.
Okay. So that's also false.
False and true is false, okay?
Yeah. True is equivalent to false or false, which is false.
Okay.
True or true implies true.
Make sure you're doing that in the right order. Do you do the implication first or the or first?
So true, true,
Okay.
true implies true. True. True or true is true implies true or true is true. True implies true is true. True is equivalent to false. That's not true, so that's false. True is equivalent to false. That's also false. False is equivalent to false, and that's true. And then true implies true is true. And true implies true is true.
Are you doing it right? Did you see those square brackets?
Yeah, so I'm going to do that first.
So you did, when you said true implies true,
That's
you were
right.
doing N implies not C, right?
Yeah.
Okay. And then you were saying not C implies W, which is true implies true.
Yep.
And then that whole thing's true, okay.
And then true implies true is true. And then W, true implies true is true. True implies true is true.
Okay. Alright, cool. Six. 6 seems to be the same thing. We want to do 6? Similar type thing?
Sure.
Sure. You want to do it?
two truths ended together is going to be true. Same thing. That's also true. False implies true is true. True implies false is false. True and true is true, and true and false is false, so this whole thing is false. True and true is true. Equivalent to true and true. That is true. P equivalent, or true and equivalent to true is true, implies false. That one's false. True implies false is false. False implies true is true. False implies true is also true. So true implies true is true. True implies false is false. False imply anything is true. True implies true is true. Implies, so this is true implies true is true. True implies false is false. So true implies false is false, and true implies false is also false. And then over here we have true, equivalent to true implies false. That's false. True is not equivalent to false, so this is false. And true implies false is false.
That's right. Okay. Let P be a sentence such that for any sentence Q, the sentence P or Q is true. What can be said about the truth value of P?
It's probably true.
Yeah. So P and Q are sentences such that, let's say that we know that P or Q is always true. We for sure know that. What can we conclude about P? That's true or false. We can't conclude anything about P. Maybe it's true, but maybe it's still false. Right? If P is you got the soup, Q is you got the salad, and I know for sure that you got the soup or the salad, what can I say about whether or not you got soup? Nothing. I still just know either you got it or you didn't.
I thought that was saying no matter what value Q is, P and or Q is always
Let
true.
P be a sentence such that for any sentence Q, the sentence P or Q is true. Oh, maybe you're right. I did read that way. Good
I
catch.
mean,
We're saying P is such that, so here's P. So P is given to us. Now, no matter what we OR it with, we're guaranteed it's going to come out true. No matter what Q we OR it with, we can plug a true Q in there or a false Q in there. So then what can we conclude about P? P has to be true. Good catch. Yep, I was reading that wrong. Okay. Let P be a sentence such that for any sentence Q, the sentence P and Q is false. What can be said now about the value of P? So I know P is a sentence such that no matter what I end it with, it's always equal to false. What can we conclude about P? P has to be false. Because we could end it with something that's true, and we're guaranteed that's going to come out false. The only way that can happen is if P is false. All right. If P is logically equivalent to Q, what can be said about the value of P or not Q? So I know P is logically equivalent to Q. In other words, I know that they're both true or they're both false. What can we say about P or not Q? Well, if P and Q are both true, then P or not Q is true. And if P or not Q, or if P and Q are both false, then P or not Q is still true. So if I know that this is logically equivalent to this, then I know P or not Q is always equal to true. I don't know why I put a box around it. Okay, next one. Let P, Q, and R be any three distinct atomic sentences. Decide by truth tables which of the following sentences are tautologies. Okay, not going to do truth tables, but maybe we can just think through it. So now P or Q are anything. Is it the case that P or Q is a tautology? Is it possible for this to be false? Yes, that could be false and that could be false. So the whole thing could be false. So it's not a tautology. P or not P, is that a tautology? Yes. If P's true, it's true. If P's false, it's true. Okay. P or Q implies Q or P. Is that a tautology?
Mm-hmm.
Yes. A couple ways you can think about that is I'll just let D be the sentence P or Q. Then that turns into D implies D. D implies D is always the case. Or you can also think about, if you know P or Q is true, do you know P or Q is true? Or do you know Q or P? I guess I switched the order on you, thinking that would fool you. Maybe that's all there was to it. Okay. Next one. To help us understand the precedent here, maybe put that like that. If you know P is true, do you know that P or Q or R is true?
No.
You do.
Yes, you do.
You do. If you know P is true, then you know it's the case that either P or Q or R is true. One of those three has to be true if you know P is true. All right. This one. If you know P is true, is it the case that not P implies Q?
Yes.
If you know P is true, not P is going to be
False.
false implies anything is
True.
true. So if P is true, then this is true. And if P is false, then the whole thing's true, because it would be vacuously true. It starts out an implication. So yeah, that's a tautology. We haven't really been marking which ones are and which ones aren't. If you know P implies Q, do you know Q implies P?
No.
No. All right. Let's do this one. If you know P implies Q has the same value as Q, do you know P? So you know P implies Q is true when Q is true, and you know P implies Q is false when Q is false. That one's making me think a little. P implies Q has the same value as Q. So we know this is true. So, if Q is true, then P has to be true. No, it doesn't. It could still be false. It could still be false. This would be true, which would be logically equivalent to that. That would not imply false. We get the true implies false there. So I'm just looking for a counterexample. So if I plug in true for Q and F for P, then this whole thing evaluates to false. Okay. I don't really want to keep going through those. I don't know. If one of you want to keep going through them, or should we go to the next ones?
I'm good to keep going.
Go to the next ones? Is that what you're saying?
Mm-hmm.
Or keep checking through
Yeah,
them?
I'm good.
All right. If P and Q are distinct atomic sentences, which of the following are tautologies? That's the same thing. On the basis of ordinary usage, construct truth tables for the sentential connectives used in the following example. Not both P and Q, neither P nor Q. Okay, so we're coming up with truth tables for these. So here's P, here's Q. And now we're going to come up with a truth table for the sentential connective, not both P and Q. And we actually have one for that. That's called NAND. P NAND Q. And I'm trying to remember the symbol for it. I think it's this. with just a line through it. I can't remember if it comes up out of it.
Is it not both the same as not P or not Q?
Yeah.
Oh, okay.
Yeah, and is the same thing as not and is the same thing as not P or not Q.
Oh, okay.
Same thing, yep. We'll make up our symbol. I'm not sure if that's a symbol, we'll make it up. This means not both this and this. So we can have true, 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 false, false, true, false, false. Alright, so if we have true and true, is it the case that I have not P and true, or not P and Q?
No, so false.
No, that's false. We have both of them. Okay, if I don't have Q, is it the case that I don't have P and Q? Yes. If I don't have P, is it the case that I don't have both P and Q? Yes. If I don't have either P or Q, is it the case that I don't have both P and Q? Yes. So there's an and. It's the negation of and. Alright, neither P nor Q. Neither P nor Q. That means we don't have P and we don't have Q.
Was there a symbol for that? I thought XOR was like exclusive OR.
No, XOR is exclusive OR.
Can't
We
remember.
don't have P and we don't have Q. Let's just write it out first and then. I don't know what to make up as a
Oh, is
symbol
the
for that.
first one XOR and then the second one's NAND?
Not both P and Q. This is exactly what we said. It means you don't have P and Q. This is the same thing as not P and Q.
Oh, XOR can't have them both be false. That's right. It'll still be true.
Neither P nor Q means not P and not Q. Or in other words, it's the same thing as not P or Q. Maybe he was trying to get us to get distribution rules from this.
Oh.
I don't know if that's what he was after. But either way, neither P nor Q I don't know, dollar sign. Whoop. All right. Neither P nor Q. There it is. So we have true, 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 false, false, true, false, false. All right. If we have true and true, is it the case that we have neither P nor Q? No. If we have true and false, is it the case that we have neither P nor Q?
No.
No. If we have false and true, is it the case that we have neither P nor Q? No. But if we have false and false, is it the case that we have neither P nor Q?
Yeah.
Yes, true. And so it's the same thing as negating the or. If we did P or Q, then we get true, 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 false. Negate that, you get false, 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 true. Okay. Give examples of sentences P and Q, not necessarily atomic, such that the following compound sentences are tautologies. Okay, so we got to turn these things into tautologies. What can I replace P or Q with to make this a tautology?
Like anything?
Anything.
Okay, P can be P or not P, and then Q can be Q or not Q.
That would work. Simpler one would just be replace Q with P. Oh no, that still doesn't work. You're right. So she says we can replace it with P or not P. And what did you say for the second one?
Q or not Q?
Q or not Q. So I'll replace Q with that, replace P with that, and now we got this is always true and this is always true, so true. Okay, next one, part B.
You can do the same thing for all of these, basically.
You can do the same thing for all of these. Replace P with something that's always true, replace P with something that's always true, replace Q with something that's always true,
It doesn't even matter.
then that comes out false, but since P is always true, it doesn't even matter. So yeah, you're right, we can just take this first P and just replace it with P or not P. plug that in for that, and then leave the rest how it is, and we'll be fine, because we'll get true or anything is true. Okay, next one. How can we turn this into a tautology?
P and not P implies whatever.
Yeah, make this P a P and not P. Make that a P and not P. P and not P is always false. False implies anything is true. Same thing down here. Replace that with that. Same thing. Okay. Is there any sentence P such that P and not P is a tautology? Can we ever make P and not P a tautology? No, P and not P is what we call a contradiction. It's always false. So there's no sentence P you can plug in there that suddenly makes it true. Okay, if P and Q are distinct atomic sentences, the sentence P and Q is a tautology implies which of the following? So if P and Q are distinct atomic sentences, then knowing that P and Q, then the sentence P and Q tautologically implies which of the following? Okay, so we're just taking one at a time. In other words, is it the case, looking at A, is it the case that P and Q implies P? Is this a tautology? Yes, if you know P and Q, you know P. What about implies Q? Is that a tautology?
Yes.
Yes. What about implies P or Q?
Also yes.
Also yes. What about implies P and not Q?
No.
No, if you know P and Q is true, then P and not Q is going to be false. And you're going to get true implies false. Not P or Q.
Yeah.
Yeah, because P and Q is going to imply Q. So if this is true, this is going to be true. And then if this is false, we don't care what that is, because the implication is going to be vacuously true. Next one. P and Q implies not Q implies P. If we know P and Q, then we for sure know P, so we know this is always true. But this could still be false. This will be false. We'll get false implies true. So no, that's false. Last one. If I know P and Q, do I know P is logically equivalent to Q? Yes. If P and Q are true, then they're logically equivalent, because they're both true. Right? Okay. If P and Q are distinct atomic sentences, the atomic sentence not P or Q, tautologically, no, it's kind of the same thing. We don't need to do another one. 17 is the last one. Is it the same kind of thing? If P and Q are distinct atomic sentences, the sentence P is tautologically equivalent to which of the following? If P and Q are distinct atomic sentences, the sentence P is tautologically equivalent to which of the following? Okay, that one might be a little bit interesting. Which of these always have the same value as P? Does P or Q always have the same value as P?
No.
No. Does P or not P always have the same value as P?
No.
No. Does P and P always have the same value as P? Yeah, if P is true, this whole thing's true. If P is false, this whole thing's false. Does P implies P always have the same value as P? No. Because P implies P is a tautology. True implies true. Yes. False implies false. Yes. Not P implies P. All right, let's think about that one. If P is true, then false implies true is true. If P is false, then true implies false is false. So that one is logically equivalent to P. So these are like simplification rules you could use. If you came across not P implies P, you know you can simplify that to just P. Same thing. All right. What about P implies not P? Is that the same thing as P? No. If P is true, true implies false is false. So P is true, but true implies false is false, so they're different. Okay, last one here. Your parentheses go right there, in case it helps. Okay, notice that this part right here is always true, right? So we're basically looking at true implies P. Is that always the same thing as P? Well, let's see. If P's true, this is true. And if P's false, this is false. So yeah, that one is. Okay, that's chapter 1 homework. We did them all. With a couple of exceptions. Not bad. You like doing the homework?
Sorry?
You like doing the homework? You think we should keep doing stuff like that? I don't know. Give me your guys' feedback as we go through this class.